This is the University of Hawaii Maui College, the college on Maui.
We will talk about some biologic chemistry today. The demigod Maui and his goddess mother Hina lived near Rainbow Falls on Hilo on the island of Hawaii. Hina would make kapa from the bark of the wauke and mamaki tree, and the strips would be dyed with magnificent designs to form cloth. The kapa, however, would still be damp when night fell, and Hina would lament how the sun moved too quickly across the sky to dry the cloth. Upon hearing this, the demigod Maui traveled to the island of Maui and climbed to the 10,000-foot summit of Haleakala, where the sun was asleep in the giant crater. Maui hid until morning and watched the sun begin his daily journey. As the first ray of sunshine appeared, Maui snared the sun with his lasso of twisted coconut fiber. The sun demanded to be released, but Maui would not let go. "Promise me you will move more slowly across the sky," Maui told the sun. And left with no choice, the sun struck a bargain with the daring demigod. The sun would move more slowly for 6 months out of the year and then move at his preferred pace for the other 6 months. Agreeing to the compromise, Maui hurried home and told his mother the good news. As a reward, Hina made her son a new cape, and sure enough, it dried in one afternoon. So our story begins in Maui and with the sun. And if you look into the day sky, just like today, you will see our very blessed sun. And it is very, very special, as we all know here on the islands. And when you look into the night sky, you will see many, many, many other suns. And they are all very special too. They are the stars. The sun and the stars have life cycles just like we do. The stars are born, they live strong, and then they grow old and die. When the ancient stars were born, there was no life, and no planets. The first ancient stars were alone, and they grew old and died. But when the ancient stars died, they left behind a very special dust, and in this dust, new stars were born. Not only were new suns and stars born into this very special dust, but now planets were born for the very first time in the dust of the first ancient stars. For all the ingredients of life were left behind by the ancient stars who were born into nothing. And in the dust of these ancient fires, we were born into paradise. And we have heard these stories time and time again. In the ancient stardust and all its ingredients of life have been studied carefully by many who are fascinated and in love with nature and creation. So don't be afraid. The ingredients of life have been organized into a table that many of us are afraid to look at. We will talk about the most important and not worry about the rest. Yes, the dust of the ancient stars gave us these elements, and we've put them on a table called the periodic table of the elements. And I know for those of you who sat in a classroom, or when I sat in a classroom, sitting in the back, we saw this table, had no idea what it meant, what it was for, and so we're only going to talk about some important ones and ignore the rest. Well, how do we know anything about ancient star dust giving us the periodic table? Well, it's the rainbows that tell us the secret about the sun and the stars. See, rainbows are just billions of prisms. Rainbows are formed by little water droplets and the sunlight passing through those little water droplets. And each of those little water droplets acts like a prism. They'll take the sunlight and divide the sunlight into its many beautiful colors. And what is happening, a prism takes light, and because light is made up of different electromagnetic wavelengths, each of the wavelengths of light is bent a little bit differently as it goes through the prism. That's how a prism, like this one here, or a water droplet, can take the light of the sun and bend it into its different spectrums of wavelengths, the different colors of light that make up sunlight. Well, we have to know a little bit about flame calorimetry. Flame, like fire, calor means heat, metry, to measure. Anything that burns has a flame that gives off light. We can burn anything, and it will give off a flame of a specific color. If we put the light through a prism, then it will form a very specific spectrum of light. And so anything that burns is going to have a very unique spectrum that we can measure. So the stars and the sun and the stars burn with very specific frequencies of light that can tell us the chemistry inside of them. And so when we look at the light that's given off the sun and the stars, we can run that through a prism, and we can see these little grooves on the spectrum that are kind of like the grooves of a record, an old vinyl LP. And these grooves on the rainbow give us specific information about chemistry that goes on not only inside of our own sun, but the stars that we see very, very, very far away. And so with very special glasses, like these glasses here on top of the Mauna Kea, the Keck Observatory, with very special glasses, we can see the entire spectrum of electromagnetic waves that are given off by the sun and the stars and many other objects out in space. And so when we talk about electromagnetic waves, light is an electromagnetic wave. But notice the visible spectrum of electromagnetic waves, light, makes up a very tiny part of the electromagnetic spectrum. Gamma rays, X-rays, ultraviolet light, visible light, infrared, microwaves, FM and AM radio waves, and long radio waves. These are all part of the electromagnetic spectrum. And all they do, the difference is just quite simply in the wavelength. How quickly the wave vibrates is the only difference between all of these things. And we can see this spectrum of electromagnetic waves, very narrow spectrum on the entire electromagnetic wave distribution. Well, everyone has a cell phone, and everyone who has a cell phone should understand that the development of those cell phones were important in us understanding how the universe was formed. Back in the old days, when they were first trying to develop the cell phones, scientists had a problem with this background frequency of microwaves. Microwaves are a type of electromagnetic wave, just like visible light, but we can't see microwaves. And so when we first started developing the cell phones, there was this frequency of microwave radiation coming from all directions of outer space. At first they thought it was pigeon droppings on the antenna or some kind of electronic problem with the antenna. And eventually they realized that these microwaves were not a problem with the antenna. These microwaves were coming from all parts of space. But to understand what those microwaves meant, we have to understand the Doppler effect, which is also important in this course as well. And the Doppler effect is very simple. When anything is giving off waves, if it moves in a direction, if it moves in a certain direction, the waves in the forward direction are more tightly together. They're smaller wavelengths than the waves that are trailing. And you guys know this. If you're driving down the road and you hear an ambulance coming towards you or a car honking its horn coming towards you, you know that as the car comes towards you, the sound is a high pitch. And as the car goes away, the sound drops in pitch. And so you'll notice if a car comes towards you honking its horn, you'll hear it go, meow. And so the pitch will drop as the car or the object goes away from us. Now, sound is not an electromagnetic wave, but an electromagnetic wave still behaves with the Doppler effect. And the reason that I bring up the Doppler effect is because right now pharmacology 203 is doing this, and before you know it, the course will be over and the course will be gone. So let's talk about the Doppler effect and the hydrogen shift. Something you should know is that stars fuse hydrogen into helium. We're going to talk about hydrogen and helium. And this gives off a very specific frequency of light. And so when stars move away from us, this light is going to be shifted by the Doppler effect. So when we look at stars and compare them to what we see in the sun, we realize the chemistry in many of the stars is just like the chemistry inside of our sun, but we can see the grooves of the record have been shifted because of the hydrogen effect, because all of the stars that we see, other than the ones in our local clusters, are moving away from us and moving away from us more rapidly than ever. So the background radiation that first bothered the cell phone developers was actually caused by a very bright light from a very large bang. And this bright light has changed from visible light and stretched because of time and the expansion of the universe because of the Doppler effect has been stretched into microwaves. Well, when I was on a jury at the courthouse, we spent a lot of time waiting, and no time being a jury. And while we were waiting, we met Anthony Natividad, who plays the nose flute. Not only does he play the nose flute, he plays the nose flute through both of his nostrils, and so he would play two flutes underneath each nostril. And the reason that he would play the flute with his nose is because the nose is something that cannot lie. And so something that he would do for us is have us stare at the mountain, which we could see through the windows of the courthouse. And as we stared at the mountain, he would play the flute in either one of our ears, in both ears at the same time. And he would tell us that if we'd stare at the mountain would whisper to us as he played the flute. And I was very impressed by that. And so, yes, the mountain does whisper the wonders of creation. And so I urge you, take a class in astronomy sometime. Astronomy is more than you think it is, and astronomy is a very important part of the University of Hawaii curriculum and the goings-on around here. But enough about astronomy. I can assure you the dust of the ancient stars did give us the building blocks of life. And here are all of them, the periodic table of the elements. And so the periodic table has 110 or more or less squares, depending on who you argue with. But we're only going to talk about a few, and we're going to ignore the rest in this class. I'll tell you right now, the periodic table is like a flat map of a round planet. If you look at a flat map of the United States, you'll see that Hawaii, the Hawaiian Islands, are off to the side out by themselves as if they're not important, and everyone knows that the Hawaiian Islands are the center of the universe and the temple of all creation, so they should be in the middle of the map, but map makers don't put Hawaii in the middle of the map for all sorts of economic reasons. So we will take the periodic table and connect one end of the periodic table to the other so we can put the important stuff in the middle rather than off to the side. So here's my periodic table of the elements. There's 103, 110 squares on this one, but we're only going to pick 4 of the most important squares on the periodic table, and those are those 4 squares right there. And so we're going to talk about hydrogen, carbon, nitrogen, and oxygen. These are the basic building blocks of biochemistry and what I want you to be most familiar with after this lecture. And so that I can give test questions away, I'll highlight things in yellow. Hydrogen, carbon, nitrogen, and oxygen, these are the basic atoms or elements of life and biochemistry. After I give the 1.2 cell phys lecture, a quiz will come up, 20 questions. 10 questions will be from this lecture. 10 questions will be from the cell phys lecture. And one of those questions will ask you about the basic atoms or the basic elements or the basic building blocks of biochemistry. And the answer must be hydrogen, carbon, nitrogen, and oxygen. How hard can it be? All right, well, I'm sure your notes say something a little bit different, but I like your notes to say something a little bit different, so you can get 2 perspectives. So let's talk about a gold coin, and let's say the coin is made of pure gold. Well, gold is an element on the periodic table. And so gold, anything made of pure gold, can be divided into billions and billions and billions and billions and billions of small gold specks. Well, eventually, I can't divide the gold anymore. Those teeny, 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 tiny little gold specks that cannot be divided, those are gold atoms. Because if we divide the gold atoms, then we will no longer have an atom that is gold. We'd have an atom that is something else. So this should be in yellow. You can get your yellow highlighter out and put this in your list of test questions. In chemistry and physics, an atom is the smallest particle that still characterizes the chemical element, just like the gold coin. If we take the gold and divide it up into teeny, 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 tiny little gold parts, then when we have the smallest part, we have an atom. And if we cut that atom in half, then we no longer have gold. So in chemistry and physics, and this class for that matter, an atom is the smallest particle still characterizing a chemical element. And something I want you to remember, atoms are very, 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 very small. An atom inside of a grain of sand is like a grain of sand on Big Beach, or any big beach. And so think about that next time you're sitting on the beach reading any pharmacology book. You pick up a handful of sand and realize that one of those grains of sand, an atom inside of that grain of sand, is just like that grain of sand on the beach, because atoms are very, very small. All right, so atoms are made up of a center, and it's a nucleus. And there's protons in that nucleus. There's neutrons. We'll talk about them in a second. But the nucleus has protons in the center. The protons are positively charged. And then the proton nucleus, the nucleus of the atom, is surrounded by an orbit of electrons. Electrons are negatively charged. Protons positively charged in the nucleus. Electrons negatively charged in orbit around the nucleus. Positive charges are attracted to negative charges, and so the proton of the atom attracts the electron that's negatively charged, but the electron spins very fast around the nucleus of the protons in the nucleus. So the type of element or atom is defined by the number of protons. When we look at the periodic table and we see a number, that tells us the number of protons, and so that's going to be the number of negatively charged electrons that are attracted to that nucleus. So let's start with hydrogen, a hydrogen atom, the smallest atom. And we'll see that it says, it's abbreviated H, and says number 1 in its little box. And so that 1 means there's 1 proton. And so 1 proton makes up hydrogen atom, and that proton pulls an electron with it. And so 1 proton and 1 electron make up a hydrogen atom. Well, let's go to the other place on the periodic table. At the top, helium. Helium is inert. Hydrogen is used all time in biologic systems. Helium is not used at all in biologic systems. So let's take a look at helium. It is inert because it does not react with anything. Helium has 2 protons, and that means it has 2 electrons in orbit around those 2 protons in the nucleus. Like I said, atoms also have neutrons in the nucleus, and the neutrons have no charge at all. That means they don't really have any electrons that follow them around. Although an element must have a fixed number of protons to be an element. If there's 1 proton in the nucleus, it's hydrogen. If there's 2 protons in the nucleus, it's helium, and so forth and so on. But the number of neutrons does not affect what type of element it is. So an element can have a variable number of neutrons. Like hydrogen, the smallest atom. It has 1 proton and 1 electron, and we can put a neutron in the nucleus, and that doesn't make the hydrogen any different. It just makes it heavier. And so hydrogen can even have 2 neutrons with the proton in the nucleus, and so all it does is make it heavier. It doesn't change the hydrogen at all, other than make the hydrogen heavier. If we change the number of protons in the nucleus, then we wouldn't have hydrogen anymore. We'd have a completely different element. So the different numbers of neutrons is the reason the atom has different isotopes. We use the word isotope all the time in medicine, like everybody has every idea what an isotope is. But quite simply, an isotope of an element is just different numbers of neutrons in the nucleus. So for the purposes of this course, you're going to need to know that protons have positive charges, electrons have negative charges, and what all that means. And so we're going to need to know about protons and electrons. But we don't need to know anything about neutrons, except for different numbers of neutrons in an atom make the different isotopes, which is a test question, I can assure you. Well, like I said, atoms are very, very small, and not only are atoms very, very small, but the protons and electrons are even very much smaller than the atoms that they create. So if a proton were the size of a guava, like a little golf ball, then an electron would be the size of a pea or a peanut in the orbit, the size of a football stadium. And so here is my football stadium. I don't know if you can see the little guava or the little golf ball in the center of the stadium, or if you can see the electron in orbit around that. But if we think about this as a hydrogen atom, if the hydrogen atom were the size of a football stadium, the proton in the center would be the size of a golf ball, and the electron in orbit would be the size of a peanut. So not only are atoms very, very, very small, but the protons and electrons and neutrons that make up the atoms are even tinier compared to the atoms themselves. So electrons are really, really, really fast. Electrons travel at 186,000 miles per second, the speed of light. Nothing can travel faster than 186,000 miles per second, the speed of light. I used to ask people this on the quiz, but nobody really liked this question. But I do want you to keep in mind that nothing can travel faster than the speed of light, the speed that electrons travel. Because electrons travel so fast, they cannot be shown to be in any one place at any one time. And so they fill an orbital shell and are said to be everywhere at the same time in that orbital shell. So when electrons travel the speed of light, we can't really point to where they are, and that has to do with the Heisenberg principle that tells us if we can tell where an electron is, we can't figure out how fast it's going, and if we can figure out exactly how fast it's going, then there's no way to tell exactly where it is. But I'll let you guys read the Stephen Hawking books to figure that out. So it's the orbital energy of the electrons. It's those electrons moving really fast that give the atom its size. Remember our hydrogen atom. If our hydrogen atom was the size of a football field, the proton would be the size of a golf ball or a guava in the center, and the orbit would be around the side of the football stadium. The electron would be in orbit around the stadium the size of a pea or a peanut. And so if we could get the electrons to quit orbiting, we could collapse that stadium into the size of the golf ball. Actually, we could collapse the Earth into the size of an orange, and that's what's going on with a black hole. Atoms have their size because of the energy of the electron in this huge orbit around the protons. And if those electrons lost their energy and were collapsed into the nucleus, we could take the Earth and collapse that into the size of an orange, making us a black hole. But again, I'm going to let you guys read the physics books about all of that. But it is important in pharmacology, and we get to those points. So here's helium, our inert atom. Helium is so stable that helium will not react with anything. Helium and the inert atoms do not have chemical reactions in normal circumstances. I think I heard a lecture from somebody who got the first person to get one of the inert atoms to react with anything, and it required all this contraption business. Inert atoms don't react with anything. It's because their electrons are in a perfect state. And if you can see my electrons of helium, they are very, very happy in orbit around these two protons. So helium is so stable, it will not react with anything. The inert atoms will not react with anything because their electrons are in a perfect state. Hydrogen, on the other hand, our smallest atom, hydrogen's electrons want to be like helium's electrons, but they are sad and they want to run away. And so with a hydrogen ion, with a hydrogen atom, with only one proton and one electron, that electron is sad, and that electron wants to run away. Well, electrons that want to run away, we put them to work in biologic systems. When an electron is not happy where it is and wants to go somewhere else, we can put that electron to work. And this is what's going on in biochemistry and biologic systems, because of moving electrons is energy. And so when we have unhappy electrons and they want to go somewhere else, we can put them to work, or at least biologic systems can put them to work. So let's ask helium. Helium, why are your electrons so happy? Well, helium's electrons are happy because two protons means there's room for two electrons. And that allows the electrons to be in pairs. So the electrons of helium are so happy because the electrons like to be in pairs. Single electrons get lonely and will run away. So, what can we do about this? Well, hydrogen only has one proton, so it can only support one lonely electron. But how about if we make two hydrogens share electrons? How can we make the hydrogen's electrons happy? Well, maybe they can pair up with another hydrogen. Maybe two hydrogens can share electrons. And so here is a hydrogen molecule, H2, hydrogen gas. And here is a hydrogen atom, one proton and one electron. And here is a hydrogen atom, one proton and one electron. But because their electrons share the houses, these two electrons are together and very happy. So each proton or hydrogen nucleus has two electrons to fill its orbital shell or its orbital house. And because they share, the electrons are happy. And so hydrogen gas is something that is relatively stable, but hydrogen gas is not inert. Hydrogen gas is very reactive. But at least we were able to form the molecule by making covalent bonds between the two hydrogen atoms. And if we had a space-filling model, it would look like that. So in chemistry, a molecule is defined as a stable group of at least two atoms in a defined arrangement that are held together by strong bonds, covalent bonds. And so the molecule is the smallest part of a substance that still retains the properties of that substance. So we made H2, which is a gas, hydrogen gas. If we split those two hydrogens apart, we would not have hydrogen gas anymore. So H2 is a molecule made up of two hydrogen atoms. All right, well, we use the word hydrogen a lot in biology, in the pharmacology business, and I don't want you to be confused. So I'll tell you right now, a hydrogen ion is just a proton. We'll talk about ions later. Ions are positively or negatively charged atoms or molecules. A hydrogen ion is just quite simply a proton. And protons in water are what make water acidic. And we'll get to that. A hydrogen atom is a proton and electron. This is almost an impossible configuration here on planet Earth because the electron is lonely and wants to run away. So even though we can define a hydrogen atom as a proton or an electron, we rarely, if never, see this configuration because of the lonely electron running away. So when we see hydrogen, we can see it as a hydrogen ion in water, a proton, or a hydrogen molecule, H2, two hydrogen atoms that come together to make a hydrogen molecule. This is hydrogen gas. Please do not confuse these three things. Well, like I said, moving electrons is the key to energy utilization. And we talk about inert atoms in this class. They're not used in biologic systems because biologic systems must be able to move electrons. Inert atoms do not react because their electrons are in a perfect state. All the other electrons that we talk about, they want to be just like the electrons that are in the perfect state of the inert atoms. And so all of this is about moving electrons because moving electrons is the key to energy utilization. We are very complex creatures and require all sorts of regulatory systems to control our energy utilization. And that's why we talk about these things in biochemistry. Electric power lines have electrons running through the metal wires because moving electrons is the key to energy utilization. And you can hear the electrons moving through the power lines. If you live close to power lines or ever close to the power lines, you can hear the electrons making a humming noise as they pass through the wires. So we were talking about hydrogen and hydrogen gas. Hydrogen gas is very rare in the atmosphere because it's very light. It will float away. However, 75% of the weight of the universe is hydrogen in one form or the other. So we talked about covalent bonds. Atoms that share electrons are covalently bonded to each other. Valences are the name of those houses that the electrons like to occupy in pairs. And so covalent means that a pair of electrons are sharing a house. And so atoms that share electrons are covalently bonded to each other. It is very difficult to separate covalent bonds, and it requires energy to do so. We'll talk about covalent bonding in pharmacology, and the thing to remember is covalent bonding means that atoms are sharing electrons. Those covalent bonds are very strong and usually irreversible in pharmacology. Well, hopefully you remember these, hydrogen, carbon, nitrogen, and oxygen. Hopefully somewhere in there you realized how it is that hydrogen makes one covalent bond. So let's talk about oxygen. Oxygen can make two covalent bonds because oxygen has two spare electrons that can be shared with other atoms. And that means oxygen has room for two extra electrons from other atoms as well. So oxygen makes two covalent bonds. And in this case, the gas O2 makes a double bond. One oxygen makes two bonds with another oxygen atom. So oxygen likes to make two covalent bonds. And in the case of oxygen gas O2, both bonds are made with another oxygen. And this is called double bonding, and it's denoted by the two lines between the O's that stand for the oxygen atoms. Or you might see it as the space-filling model. Two oxygens with O2 gas are double bonded with each other. See, because oxygen's electrons want to be like neon. Here's neon. And neon is completely inert. Neon will not react with anything because its electrons are happy and in a perfect state. Neon has 5 happy houses of electrons. There's a pair of electrons in the center house, and then there are 4 pairs of electrons around the 4 houses around the side of neon. And oxygen wants to be like neon. Its electrons want to be like neon's electrons, perfect and happy. So oxygen has two houses where the electrons are not happy. So oxygen has happy electrons in the center, happy electron pairs there, and happy electron pairs there. But oxygen has a lonely electron in one house and a lonely electron in another house. And so what can we do to make those electrons happy? Well, 2 oxygens in this case can come together and they can share electrons covalently bonding with each other in 2 places, double bonding, and now all our electrons are paired and in a perfect state and very happy. But oxygen gas is not inert either. And if we did that with a space-filling model, it would look like that. So oxygen gas is O2. Oxygen gas is present in the atmosphere at about 21%. FiO2, the fraction of inspired oxygen, is 0.21. Those of you going in the healthcare business, you definitely want to know this right here. O2, which means 2 oxygen atoms covalently bonded to each other, double bonded with each other to form oxygen gas, is present in our atmosphere at about 21%. And 21% is the same fraction as 0.21. So what happens when you mix oxygen gas and hydrogen gas? Nothing. But what if we add some activation energy by adding just a little spark or a little flame to the oxygen and hydrogen gas? Well, big explosion is what you get. You'll get fire and water, and everyone misses that on the quiz, and I'm not sure why. However, the oxygen and oxygen gas and hydrogen gas combust to make fire. The main shuttle engines burn hydrogen and oxygen gas. The exhaust of that burn is water. So hydrogen gas and oxygen gas will burn together to form water. and they're stored in that big orange tank as liquid. And so the space shuttle will store oxygen as a liquid and hydrogen as a liquid and have them form with fire to make energy in water. And so water is H2O. Burning hydrogen gas, H2, and oxygen gas results in water. And here's the chemical equation for those of you keeping score. 2 hydrogen gas molecules plus 1 oxygen gas molecule will burn to form 2 molecules of water. So water is H2O, 2 hydrogen atoms covalently bonded to an oxygen. And that makes sense. Remember, hydrogen makes 1 covalent bond, and oxygen makes 2 covalent bonds. And so you guys should already know all the chemistry you need to know about water. But something else you should know about water is the molecule is not flat. This course would be a lot simpler if water molecules were flat, but water molecules bonding at angles is essential to life on Earth. And so we need to talk about why that is important. And notice the hydrogen bonds. Notice the covalent bonds are noted by these little lines there. So notice the covalent bonds are at angles. They're not flat. So even though the oxygen and hydrogen each share an electron, the oxygen, remember, has electrons that it has kept to itself. Because the oxygen has those unshared electrons, that leaves the oxygen part of the molecule more negative and the hydrogen part more positive. All right, so again, here is my oxygen atom. Remember, we had the pair of electrons in 2 of the houses. Up here, there's a happy pair in the center, and then these happy pair up at the top. And then we have a lonely, sad electron here and a lonely, sad electron there. And one of the things an oxygen atom can do is combine with 2 hydrogens to share those electrons. And so those electrons can be happy. And now we have H2O. However, remember these 2 happy houses of electrons, because those electrons did not combine with anything, and because electrons are negative, this makes the oxygen side of the molecule more negative, and this side of the water molecule more positive. And this is why water is called polar. Water is polar because one side of the molecule has just a little bit more negative charge than the other side of the molecule, which has a little bit more positive charge. So water is polar because the extra electrons on the oxygen side of the molecule, that makes the water molecule polar. Well, because water is polar, it attracts molecules that are polar, and it attracts charged ions as well. And we're going to talk about charged ions here in a little bit. Because water is polar, it's going to repel nonpolar molecules like hydrocarbons. Hydrocarbons are lipids, fats, oils, waxes. You know that water and oil don't mix easily. If you've ever seen the salad dressing, you have to shake it up to mix the water and the oil for temporarily, because water attracts polar charged molecules and water rejects nonpolar molecules like hydrocarbons, lipids, fats, oils, waxes. So water is polar. Hopefully you'll remember that. And because the water is polar, the hydrogen of one water molecule is going to be strongly attracted to the oxygen of the other molecule. And so notice, here's one water molecule, and here's the other water molecule. And so this water molecule right here, the oxygen, is covalently bonded to 2 hydrogens. Here is my other water molecule. Notice this oxygen is covalently bonded to these 2 hydrogens. But notice this hydrogen of one water molecule is strongly attracted to the oxygen of the other water molecule. And that strong attraction is called hydrogen bonding. And I will ask you lots of questions about hydrogen bonding on your quiz and your exam. Hydrogen bonding is not as strong as covalent bonding, but hydrogen bonding is still strong. And hydrogen bonding is important not only in biologic systems, but our understanding of pharmacology. Sometimes the hydrogen bonds, instead of being nice animated hearts for that strong attraction, sometimes they're just shown with boring dotted lines like I have here. And so hydrogen bonds are shown with dotted lines, and that's something to keep in mind. I asked a question about hydrogen bonding, and a lot of people miss it because they confuse the hydrogen bonding between two different molecules with covalent bonding, which is going on in one molecule. So notice here's a water molecule. The oxygen makes two covalent bonds with two hydrogens. Each hydrogen makes one covalent bond. So here's one water molecule. Here's another water molecule. And notice the oxygen of one water molecule is attracted to the hydrogen of another water molecule. That's hydrogen bonding. So hydrogen bonding can actually occur between any oxygen and just about any hydrogen of another molecule. And to make things especially confusing, hydrogen bonding can occur between a hydrogen and a nitrogen of another molecule as well. So there are more places to have hydrogen bonding than just between water. But I use this example because this is a great example. Well, the Hindenburg was a blimp, and it was filled with hydrogen gas. The hydrogen gas was light and made the Hindenburg float. But the other thing that hydrogen gas did was make the Hindenburg very explosive. The Hindenburg caught fire and burned in about a minute. Something you should do is go to YouTube.com for all sorts of reasons. But one of the things that you should do is put in Hindenburg into YouTube, and in about a minute you'll see this giant blimp explode and burn to pieces, burn to nothing in a matter of seconds. And the point is that oxygen and hydrogen burn together and release enormous amounts of energy. But biologic systems must control that burn in a very slow, efficient, stable manner. Biologic systems combine hydrogen with oxygen to release energy. But biologic systems cannot release that energy all at once, as in this situation. Biologic systems must control that burn very, very slowly, very, very efficiently, and in a very stable manner. See, biologic systems are masters of efficient, renewable energy use. And the question leads to, why aren't we? So to control the burning of hydrogen and oxygen, rather than have them combine as gases and result in a big ball of fire, we attach hydrogen and oxygen to carbon. We use the carbon as a backbone or a skeleton for biologic molecules. And so what happens? What do you see? What do you get after the fire dies? So what's left over after the fire dies? Well, a lot of the gray stuff is phosphate. However, the black stuff is carbon. The oxygen and hydrogen have been burned up, but rather than exploding in a gas, they burn more slowly and more efficiently because the hydrogen and oxygen were attached to carbon backbones. So the hydrogen and oxygen were not in the gas form. They were in a molecular form bound to carbon. And so those logs that burned in the fireplace, those logs are made up of carbohydrates, which you've all heard of before. Yes, carbohydrates are sugars and starches, and something else, wood, is made of cellulose, and all of these are carbohydrates. Carbohydrates are just quite simply chains of glucose molecules. And glucose molecules are just carbon chains with oxygen and hydrogens attached in such a way so we can release the energy in a very efficient manner. You should know at this point in your careers that we use glucose or sugar for energy. And the energy comes from the hydrogen and the oxygens, and we're able to burn them in a very efficient manner because they're attached to a carbon chain. And all of these things are made by the sun, photosynthesis, to make things with light. Plants put the carbohydrates together for us using photosynthesis. See, I knew that story about the sun was important. Well, hopefully you remember these. Hydrogen, carbon, nitrogen, and oxygen are four basic building blocks of biochemistry. Remember, hydrogen makes one covalent bond. Oxygen makes two covalent bonds. So let's talk about carbon. Carbon is a very unique substance. Pure carbon can be in the form of a black powder like coal or graphite. Pure carbon can be formed into a diamond as well. But in biologic system, carbon makes four covalent bonds. And so here is my carbon atom. And in the center are two happy electrons paired together. But each of the four houses around the side contain an unhappy electron and with room to share electrons. So this is why carbon makes four covalent bonds. So carbon likes to make four covalent bonds like the hydrocarbon gas methane. Notice here is my carbon, and notice that it's making four covalent bonds, and those covalent bonds are with a hydrogen. Remember, hydrogen makes one covalent bond, and so this is the molecular formula for methane, and if you have the Chemistry Tinker Toy set, it would look like that. Carbon making four covalent bonds with four hydrogens. So carbon likes to make four covalent bonds. Here is the gas carbon dioxide, CO2. Here, notice, the carbon is making four covalent bonds, and it is making these covalent bonds with oxygen. Remember, oxygen makes two covalent bonds. So here is a double bond between the oxygen and the carbon. And here is a double bond between the other oxygen and the same carbon. And if you had the Tinker Toy space filling set, it would look like that right there. Well, here's what's confusing. Because carbon is the backbone of biologic molecules, it's not even shown in molecular diagrams. When we look up information in pharmacology, they're going to show us these little stick figures, and they just assume that we know what those mean. Because carbon is the backbone of biologic molecules, it's not even shown in molecular diagrams. We just assume they're there. And if a bond is ever missing from the carbon, then we assume that it's attached to a hydrogen. So let's go through that. You might see this somewhere on a molecular diagram. Can you see where the carbon atoms are? The carbon atoms are at each of those angles. And so this is where the carbons are, at each of those angles. And we'll go ahead and put the oxygen up there as well. And so the oxygen has made two covalent bonds, but notice each of the carbons is only making two bonds. And we know that carbon makes four, so that must mean there are hydrogen atoms somewhere on this molecule. And so to make carbon have all four covalent bonds, that means each of these carbons must have two hydrogens attached to it. So this is obviously very difficult to draw in a book. It's much easier to do with PowerPoint. And so since they can't draw molecules to look like that in a book, and it's difficult and time-consuming to make it look like that in a book, they'll take this molecule and draw it just like that in a shorthand notation. And so when you go through pharmacology and do research in pharmacology, and they show you molecular diagrams, this is what those diagrams mean. I wanted to show you aromatic rings. Carbons can shift double bonds from carbon to carbon. Like here is an aromatic ring. And I've animated it so you can see the carbon atoms shifting their double bonds from carbon to carbon. Maybe you don't see the carbon atoms. Well, I'll give you a hint. They are right there at each of the corners. So an aromatic ring is 6 carbons, and the carbons are shifting their double bonds back and forth between the adjacent carbon. Well, if you count carefully, you'll notice that each carbon is only making 3 covalent bonds, and we know carbon needs to make 4, so we can assume that there is a hydrogen attached to each carbon on the edge of the ring. The thing about aromatic rings is they're very stiff and hold their shape. They're not flexible at all. So aromatic rings are everywhere in biologic systems, and we will see aromatic rings more than once in this course. But they don't draw these diagrams with the carbons. They just leave the carbons out and assume you know enough about chemistry to assume they're there. So when you see this ring structure, you'll know what that means. And of course, they don't animate the double bonds. They'll draw them like this. They'll draw a circle in the center of that aromatic ring. Or they'll draw them just like this without them being animated. And the reason that I talk about this is that aromatic rings are everywhere, like the amino acid tyrosine. We're going to talk about amino acids in the next lecture a lot. And so here's tyrosine, an amino acid. And you can see our aromatic ring right there. Each of these corners is a carbon atom. And then we can see this group and that group and another group right there, and we'll talk about that right now. And it's very difficult to draw tyrosine, the amino acid, like this. That's why they use that stick figure shorthand, leaving out all the carbons and hydrogens. They draw it just like this. So tyrosine is an amino acid, and we'll talk about tyrosine when we make the catecholamines. But this is the generic formula for all amino acids. R just means a variable group. R can mean any kind of variable group. So an amino acid has an amino moiety, which we're getting ready to talk about, a carboxylic acid moiety, that's where the amino acid comes from, and a variable group. R just means variable. So when you see any molecular diagram that has an R, that means it can be anything. And so an amino acid is always going to look like this. It's going to have an amino group. It's going to have a carboxylic acid group. There's going to be a carbon in the center of that. We call that an alpha carbon. And then it'll be attached to the R group. So R just means any variable set of atoms. A moiety just means a functional group of atoms. The reason that carbon is shown right there is because if it's part of an acid group, it's not part of the backbone. It's part of an acid group, an acid moiety. So that's why it's shown. And don't forget about that carbon in the center that they don't even show in the amino acid. That alpha carbon is in the center of the amino acid, and it's very important. So an amino acid, that alpha carbon in the center, is attached to the amino group. We'll get ready to talk about that. Carboxylic acid group, we'll talk about that too. The R group, which is the variable group, and then another hydrogen atom, remember, because the carbon has to make 4 bonds. And so I ask you this question only so that I know that you made it at least this far in the lecture. But amino acids are very important. If you get on Wikipedia and look at their explanation of amino acids, you might come across this picture right here. For the basic science stuff that I've been talking about, Wikipedia is an excellent source of information. If you have any problems or confusion about anything I've talked about, or you want to know lots and lots of information about this, you can get onto Wikipedia and take a look at that. So again, this is drawn differently. Here's an amino acid. There's the amino group. There's the carboxylic acid group. There's the alpha carbon in the center. And attached to that alpha carbon is a hydrogen atom and the side chain, the variable group. So I just wanted you to see what moieties were, what that R stood for. And again, carbons make 4 covalent bonds. Well, hopefully you haven't forgotten the star of our show, hydrogen, carbon, nitrogen, and oxygen. Hydrogen makes 1 covalent bond. Carbon makes 4 covalent bonds. Oxygen makes 2 covalent bonds. Now it's time to talk about nitrogen, our electron juggler. So the nitrogen atom has 3 places where it can make covalent bonds. It has a happy pair of electrons in the center, happy pair of electrons on the outside, and 3 places where the electrons are single and not happy. So since nitrogen can make 3 covalent bonds, we can talk about nitrogen gas, N2. The nitrogen is triple bonded with the other nitrogen atom, and so the 2 nitrogen atoms make N2 nitrogen gas. And that triple bond between the nitrogens is very, very, very strong. And if you had the Tinker Toy space-filling model, it would look like that right there. Well, nitrogen is a very unique element. Nitrogen gas is the most common gas in the air. It's about 80%, 79%, for those of you who are going to send me an email telling me it doesn't add up. And the triple bonds between the 2 nitrogens are very, 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 very strong. Which leads us to nitrogen fixation. Nitrogen gas, which is almost inert, can be converted into biologically useful nitrogen by fixation. To turn nitrogen gas into something that we can turn into use in biologic systems requires fixation. Remember our nitrogen in the amino acid? How do we go from nitrogen gas to nitrogen that we can use in biologic systems? Well, that's done by fixation. In the old days, it was exciting to think about lightning accounting for nitrogen fixation, but that's not where most of the nitrogen comes from. It's bacteria in the soil that can convert nitrogen gas into things like amines and other useful nitrogens that we use in biologic systems. And this, too, is something that I will ask you on your test. And there's the yellow print we've been looking for. Nitrogen usually makes 3 bonds, but nitrogen can also make a 4th bond. And this gives the nitrogen a positive charge. And this is very important in biologic systems and in pharmacology. So nitrogen makes 3 bonds, but when nitrogen makes that 4th bond, this turns nitrogen into a positively charged ion. And so let's go over that. Hopefully you haven't forgotten about these. Hydrogen, carbon, nitrogen, and oxygen. Hydrogen makes 1 covalent bond. Carbon makes 4 covalent bonds. Nitrogen can make 3 covalent bonds, and nitrogen can make a 4th covalent bond, making the nitrogen positively charged. And oxygen makes 2 covalent bonds. So here again is my nitrogen atom, and remember it had 3 places that it could bond, and a happy pair of electrons right there. Well, let's take this amino group. Here, the nitrogen has made 3 covalent bonds. Here, with anything, R can mean anything, and so that's attached to something. The 2 hydrogens make up the rest of the nitrogen bonds. And so here we have nitrogen making 3 covalent bonds. And this happy pair of electrons right here, once the nitrogen has made these 3 bonds, it can make those happy pair of electrons greedy and wanting to steal a proton away from another molecule. And so this is how nitrogen can make the fourth covalent bond, because these two electrons can get greedy and try to attach to another molecule. Here is our carboxylic acid moiety. And here, those greedy electrons can steal the proton right away from the molecule, making the nitrogen positively charged. And because we took the positive charge away from the carboxylic acid, we're left with two greedy electrons looking for another proton, and our carboxylic acid here is negatively charged. So things that are positively charged and negatively charged either have an excess number of protons or an excessive number of electrons, leading to either the positive or negative charge. So moving protons around is the game of acids and bases. You're going to talk about all sorts of acid and base stuff in the healthcare business, and something that I wanted you to know right now is moving protons from one molecule or to another is the game of acids and bases. And moving protons causes electrons to move as well. And remember, moving electrons is the key to energy utilization. And so we talk about all this biochemistry business so that you understand that all of this is about utilizing and manipulating energy. All right, like I said, ions are either positively and negatively charged. Here's ammonium. Because the nitrogen has made 4 bonds, the nitrogen is positively charged. Positively charged ions are called cations. I can assure you that's a test question. Here's a hydroxide ion. It is missing something right there. Those pair of electrons make it negatively charged, and so the negatively charged ions are called anions. And the anions are created by either protons being stolen or extra electrons hanging out. So any substance that releases a hydrogen ion into the water is called an acid. And so you'll see a hydrogen ion, abbreviated H positive, and all that is a single proton in the water. Any substance in this course that releases that proton, that hydrogen ion, into the water, we're going to call that an acid. We're going to talk more about acids in upcoming lectures. Any substance that can take the hydrogen ion or the proton out of the water is considered a base, like this hydroxide ion. Notice with that negative charge, what is it missing? It's missing a proton. Hydrogen can go right there. And so what happens when you mix acids and bases? Well, in this case, they neutralize each other and leave us with water. So let's talk about oils, lipids, fats, hydrophobic, lipophilic substances. Hydrophobic means to hate water. Lipophilic means to like fat. So hydrophobic, hating water, lipophilic, liking fat, they're the same thing in this course. These substances are repelled by water. So be careful using words like hydrocarbon. Hydrocarbons are quite simply carbons with hydrogens. Carbohydrates are sugars and starches, and those are carbons with hydrogen and hydroxide groups attached to them. And we use carbohydrates for our primary source of energy. They talk about saturated hydrocarbons all the time, like you know what those mean, like saturated fats. Saturated just means that the carbon chain is completely full of hydrogens. That means there's no double bonds in the carbon chain. So unsaturated hydrocarbons must mean the carbon chain is not completely full of hydrogens. That must mean there is a double bond somewhere in the carbon chain. Because there's a double bond in the carbon chain, that means that unsaturated fats, unsaturated hydrocarbons, since they're crooked in shape, they don't stack and stick together really well. That's why they talk about saturated fats sticking together and clogging your arteries, and unsaturated fats being better for you because they don't stick together so well because of those double bonds, and they don't clog your arteries so well. They talk about saturated and unsaturated fats on TV like you know everything about them, but I bet you didn't know that whether they're saturated or unsaturated quite simply has to do with whether those carbon chains are full of hydrogens or those carbon chains have double bonds somewhere. So I showed you methane. Here's my carbon making 4 covalent bonds with 4 hydrogens here, each the hydrogen making 1 covalent bond. Methane, this is ethane. Propane, you guys should know what propane is. This is the very difficult way to draw propane. This is the very simple way to draw propane. Yes, the same propane that's in the grill is a hydrocarbon with 3 carbons, and the propane mixes with the oxygen in the atmosphere to make fire, carbon dioxide, and water. Here's octane. Octane is something in gasoline. They compare how your gasoline burns with octane. Octane has 8 carbons, and rather than draw all that with PowerPoint, we just draw it with the stick figure. So when we talk about hydrocarbon chains, we're talking about non-polar substances. Remember, water and oil don't mix, and so water repels non-polar substances. That means hydrocarbons repel water, ions, and other polar substances. Molecules that are not charged or polar, molecules that are not charged or not polar are lipophilic. Lipofat, philic to love. That means they like fatty, oily, waxy, or greasy substances. Oh, why, Dr. Farmer, why are we discussing all this? Well, to discuss pharmacology, we must understand ions, and those are charged atoms or molecules. We must understand the concept of acids and bases, moving a proton from one place to another. We must understand what polar means. Water is polar because one side is more positive than the other. Hydrophilic, meaning water-loving, versus lipophilic, fat-loving. We need to talk about phospholipids, the building blocks of cell membranes. We need to talk about amino acids, the building blocks of proteins. And we need to talk about nucleic acids, the building blocks of DNA. That's why we talk about all of this. All right, so the periodic table is like a flat map of a round planet. So I'm going to take 2 periodic tables and put them next to each other and put my perfect elements right in the center of the map, and that'll give us a better perspective of what's going on. So here are my inert elements right in the center of my periodic table where they belong. And there are my 4 basic building blocks of biochemistry. Notice hydrogen is 1 step away from perfection. Hydrogen makes 1 covalent bond. Carbon is 4 steps away from perfection, 4 bonds for carbon. Nitrogen is 3 steps away from perfection. That's why nitrogen makes 3 covalent bonds. If nitrogen makes the 4th covalent bond, the nitrogen is positively charged. Oxygen is 2 steps away from perfection. That's why oxygen can make 2 covalent bonds. Something interesting to know about oxygen is what is right underneath oxygen. Sulfur. Sulfur is 2 steps away from perfection, so sulfur can make 2 covalent bonds, and sulfur is very similar to oxygen. And you would know that if you studied the volcanic vents that are so amazing that are right between us and the Big Island. The volcanic vent life forms get their food in such a way that these microscopic creatures that are fed on by these systems, they use sulfur as a substitute for oxygen. Down deep, there is no oxygen, and so the bacteria have been able to use the sulfur from the volcanic vents and utilize the sulfur just as if it was oxygen. And the reason they're able to do that is because oxygen and sulfur are 2 steps away from perfection. That means they can make 2 covalent bonds. That means sulfur can be a substitute for oxygen in very specialized creatures like the ones that feed these life forms in the volcanic vents. And there's another picture of volcanic vent life forms that use the bacteria that they feed on use sulfur instead of oxygen in their metabolism. Well, let's talk about sodium chloride. That's what makes up table salt. Notice sodium is on one side of perfection. Chloride's on the other side of perfection. And so when they're out of the water, they can team up to form sodium chloride. And so sodium has one more proton and electron than neon. So sodium's lonely electron runs away quickly in water, resulting in a sodium ion. And chloride has the exact opposite situation. Chloride has one less proton and electron than argon, so chloride has an extra space for the lonely electron, resulting in a chloride ion. So sodium chloride is table salt. It's the same stuff you find right there. If we put sodium chloride into the water, they're going to divide up into their respective ions. Because water is like a single club for lonely electrons. And so if we take something like salt and put it in the water, it can divide right up into its different ions. Just like potassium chloride. Potassium chloride, they sell it as a salt substitute. It's a salt. Notice the potassium was one step away from perfection. The chloride is one step away from perfection. That's why the potassium chloride is able to bind with each other right there in the salt substitute. Potassium chloride is a salt, I assure you. And when we put the potassium chloride into the water, the potassium and the chloride can divide into potassium ions and chloride ions. I assure you it's essential that you understand sodium ions, potassium ions, and chloride ions when we start talking about pharmacology. Here's magnesium and calcium. Notice they're 2 steps away from perfection. That's why calcium and magnesium form double charges in water. And they form those double charges because of their 2 steps away from electron perfection. But here's something I wanted you to know about. Phosphorus. Phosphorus is an electron juggler just like nitrogen, but phosphorus is a very powerful mover of electrons. And so you might hear about the inorganic phosphate. If we take that phosphorus, we can attach it to 4 oxygens and form an inorganic phosphate. That's 4 oxygens with 3 negative charges. Yes, the phosphate is a very powerful mover of electrons. And because phosphate is a very powerful mover of electrons, phosphate is essential in energy transfer. Remember adenosine triphosphate, ATP, the essential energy currency of the cell. It is that 3rd phosphate that provides an enormous amount of energy for chemical reactions inside the cell. Something I want you to keep in mind before the next lecture, any enzyme that can move a phosphate onto or off of a molecule, it's called a kinase. Kinase comes from a kinetic, which means to move around. And we're going to talk about enzymes in our next lecture. All right, well, if this lecture was too easy for you and you know everything that I've mentioned and you found yourself bored, then you need to go buy these books and you need to memorize them. Katzung's Basic Clinical Pharmacology is designed for MD and PharmD students. It's very difficult to read and understand. If you have an excellent biology background, an excellent science background, you can read this book. My predecessor used to use the Katzung book, and the students started emailing me telling me that the board review book is much easier to read, full of all sorts of great questions and more to the point. And so these books are optional. If this lecture was too easy for you and you understand all this information, you need to get one of these books and memorize them, if not both of the books. However, everything that you need to succeed in this course will be available to you online. So please do not buy the books if you cannot afford them or you do not plan to read them. Well, that is more than enough time for this lecture.
This is Cable 55. Maui College Television Network.
In historical times, palms have been a symbol for victory, peace, and fertility. Today, they are a symbol of luxurious tropical vacation spots. A third of the world's population depends on coconut to some degree for their economy. The coconut palm tree, known to some cultures as the tree of life, is highly valued as a source of food that is rich in fiber, vitamins, and minerals. Coconut derivatives are also used in the production of medicine and is considered by some to be the cure of all illness. The palm tree is known to have many uses. Here are some examples for products that have been made from the different parts of the tree. Like many other trees, palm trees need to be trimmed in order to produce higher quality fruits. Proper trimming improves the size and quantity of the crop as well as the health of the tree by removing dead or dying branches. Unfortunately, there are some trimming methods that are quite harmful for the tree. The foot spike method, for example, leaves spike wounds on the tree trunk that never heal up, only become bigger and bigger while exposing the core to harmful bacteria and disease. What's unique about the spikeless trimming equipment is that it includes platforms that are made with rubber straps that wrap around the tree trunk and therefore enables one to climb the tree without causing any harm.